All right, guys, it's time for Fun with Math. And today, I want to go over first some homework with you before we get into the lecture activity. So this was the assignment, quadratic functions and models, part 2. So let's take a look at a few of these problems because a couple of them may be kind of tricky, especially the first one. So the first one is actually a calculator problem in disguise. So if you try to do this by hand and solved it, that's actually quite a feat because the function right here, which I'm going to rewrite so you guys can see it a little bit better, f of x equal to negative 0.1 x squared, that point better, and then plus 1.4 x plus 8 is kind of hard to work with because it has these decimals on it. Now, you can get rid of decimals by factoring out a 0.1, but that's a little tricky to do. So this problem is actually designed for you to use your calculator. So what we actually have here, it says a ball is thrown upward from a height of 8 feet. The height of the ball, f of x, in feet can be modeled by the function that I just wrote down, where x is the ball's horizontal distance in feet from where it was thrown. Use this model to solve parts A through C. So for part A, what do we want to do? We want to find, it says, what is the maximum height of the ball and how far from where it was thrown does this occur? So we basically want to find the vertex of the quadratic function. So to do that, we're just going to use our graphing calculator. So I'm going to graph this. And notice they kind of gave us the graphs down here. So one of these graphs is going to be correct. So you can kind of see how to graph it. And so on your calculator, if you have it, pull it out, hit y equals for me, and we're going to plug this in. So it's negative. So make sure you hit the negative button, 0.1. And then we have an x squared, so x squared. And then we're going to add 1.4 times x, and then plus 8. And so there's my y equals, and then I'm going to make my window. Now to make my window, I'm going to come down here, and I look at these input values. So I'll notice all the input values are the same. They're all going from 0 to 25, and the output values are also going from 0 to 25. So I'm just going to use these graphs to tell me basically what to do. And so this would go from 0 to 25, and y min would go from 0 to 25. And then we can just hit graph, and we should see the ball go up and then come down. So there it is. The ball went up, and then it came down. So we can copy this graph down right here. So here's my graph. It goes from 0 to 25. I have my x and my y, and it goes from 0 to 25. And basically, it starts up here, comes up, and goes down. And there's actually an arrow here, although it actually stops at the ground. So we'd probably stop this as soon as it hit the ground right here. So stop here and start here. So you don't actually have to put arrows on there because it's an actual ball. So it goes up, comes down. I guess it bounces at the end too, right? Which is not modeled by this function. And so now we want to find the vertex here, which is the maximum value. And so on my calculator, what do I do? Well, I'm going to hit second trace and then go down to maximum, and I hit enter. And then it's going to ask for a left bound and a right bound. So I'm going to scroll over to the left here. So just keep scrolling over to the left. And when it gets to the left, the maximum, I hit enter. And I scroll over to the right. And then hit enter again. And then enter for a guess. And it's going to spit out some numbers. So basically, it looks like 7 and 12.9. So right here, I'll put a 7, comma, 12.9. And then for the max height, well, what's the max height equal to? Well, the height, that's not the input, that's the output. So the maximum height is 12.9 feet. And so right here, I just plug in 12.9. It already has a feet on there. And then which occurs, and so now they want the input that goes there, which occurs 7 feet from the point of release. And that's part A. And then for part B, what do they want? It says, how far does the ball travel horizontally before hitting the ground? And so there it is where it hits the ground, and that's when it has height 0. So now we're basically going to take this function, this quadratic function, and set it equal to 0. And we can use our calculator to do that. We'll just use the 0 button on the calculator. So we saw this button before. And so on your calculator, just hit second trace and then go down to 0, hit enter. And again, it's going to ask a few questions. It wants to know a left bound and a right bound. So we need to get to the left of the 0. So I'm going to scroll down. In fact, I'll scroll down. I'll even pass the 0 so you can see me pass it. All right, so I passed the 0. So it's kind of hard to see, but look at the outputs, how they're negative and now they're positive. So there's my cursor. I hit enter. That's definitely to the left. And then for a right bound, I have to pass that 0. So when the outputs go past 0, there it goes. It's definitely negative. The outputs are negative. And I hit enter again for a guess. It'll pop right onto it. And then notice this number right here, that -1 e to the -12. That's kind of a curious number, -1 with an e and a -12 next to it. That's actually equal to -1 times 10 to the -12, which if you're not familiar with scientific notation, what that means is there's a decimal right here. Move that 12 places to the left. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I think, if I count that right. That's what that number is equal to. So basically it's 0. That's what it's saying. So they're saying this number right here is something, comma, something, and they want this to the nearest tenth. And so it's something, comma, 0. And so what was the something? I have to go back and look at my calculator again. So my calculator says it was 18. If we round to 1 decimal place, the second is a 5, so we round up. So 18.4. So 18.4. So that would be x equals 18.4 feet. And so over here, you'd put 18.4. It already has the feet on there. And now for the last question, part C, they're asking us which graph models the ball's parabolic path. Choose the right graph below. And so notice the maximum is just 12.9. So that's too tall. That looks a little bit too small. This looks just about right. So I'm going to circle that one thinking that's probably right. And that's too tall. Yep. So it must be C. All right. So we'd fill in that little dot right there. All right, so that's a nice little calculator problem that a little tricky to do by hand. If you wanted to do this by hand, you'd actually factor out a -0.1 would probably be the easiest way, and then set this up, plus what you do the blanks, and then basically this is going to be x squared, and then these pluses actually, because you factored out a negative, they're going to become minuses. So it's actually going to be x squared minus and the minus, and this will actually be 14x, and this will be 80. And this guy you can kind of work with, but you still can't factor it. Okay, so you actually, to solve this, you have to use the quadratic formula, which then you'll need a calculator too, or you could complete the square, which is a little tricky. So again, this is really a calculator problem. All right, there's one last problem I want to look at with you guys. So down here, number 4. Let's do this one together. So this is a nice little problem. And so what does it say? It gives us the picture here. So here's my picture. In fact, I think I might just make this picture a little bit bigger over here. So they give us this picture here. It's divided into 6 pieces. So there's our 6 pieces. And it says you have 600 feet of fence to construct 6 corrals. So I have 600 feet of fence. And we want to find the dimensions that maximize the area enclosed. What is the max area? So we want to find first the dimensions that give us the max area. And we also want to then, in the end, also find the max area. So you basically want to find everything for this problem. And they even label the sides for us. So they say, the horizontal side is x. So these are going to be my x's. So I have an x here. I have an x here. And I have an x up here. And then I have y's vertical. So y, a y, and another y. And the equation I'm looking for is something to maximize or minimize my area. In this case, I'm maximizing. So a is equal to x times y. And the big idea is you'd like to graph this formula, but you can't because you have x and y. So we have to get rid of y. So that's where the 600 is going to come into play. So 600 is going to be equal to, and you just count it up. And so you count up the sides. It's the perimeter of the corrals, basically. So all the fence. So you have x feet there, x feet there, x feet there. So that's 3x, and then plus, and then count up all the y's. You have y feet plus y feet plus y feet plus y feet. So you have 4y feet. And then you can solve this for y, and we can then substitute in there basically. So we'll subtract 3x from both sides. And so we get 600 minus 3x is equal to a 4y. And then we'll just divide out both sides by 4, and that'll give us y. And so 600 minus 3x, all divided by 4, is equal to a y. And so now we just plug that in for our y over here. So a is going to be equal to x times, and we have 600 minus 3x divided by 4. And now we can solve by simply graphing this thing. So take out your graphing calculator here. So where's my calculator? There it is. We'll turn this on. We'll hit y equals. We'll clear this out and just plug in. So we have x. And then it's kind of tricky to plug this in. So to plug this in, remember, these parentheses you actually don't need, but you are going to need parentheses on top because that's all in the numerator. So what we have to do is we have to add an extra set of parentheses kind of on top. You don't need the outside ones, though, if you don't want them. So 600 minus 3x in parentheses, and then divide by 4. So that's how you put it into your calculator there. And I should have an x in front. Do I have it? Yeah, I have an x there. Okay, now make your window. So here's where you have to really kind of think. So I'm going to definitely start at 0. Then how big do you want to make it? Well, remember, you have 600 feet of fence. So if you go to 10, it's probably not big enough. So, maybe I'll go to let's do 200. You could try 100 first if you want, but I think it's probably going to be a little bit bigger. Let's try 200. It's got to be reasonable. It can't be like 2 billion. And then you're going to hit zoom and then go to zoom fit. So just go all the way down to 0 and hit enter on zoom fit. And we really want to see this come up and then come down somewhat. And that looks great. Actually, that's actually perfect. So 0 to 200. Here's my x, and I'm getting out a stuff. And it basically just goes up. And it looks like it actually comes down right at 200. And what we want to do is we want to find that maximum, basically looking for the vertex of the parabola. And so we go back to our calculator. We hit second trace. We go down to number 4, which is maximum. Hit enter. And then it's going to walk us through it. And actually, we wound up right on it because we found the perfect x value. But go to the left of the maximum, hit enter. And I'll scroll up back towards the maximum. So somewhere up there, there's the maximum. I'll go to the right because it says right bound. And then it says guess. So I hit enter. And it pops right on it. It's 100, 7,500. And so what do I know now? I now know a couple things. I know what x is equal to. And so x is equal to 100. So for right here, I'll put x is 100 feet. And then it wants y. Now here's where we have to be really careful. So y is equal to, so you probably want to put this as y, but remember, that's not y, that's area. So to find y, we have to come back to the formula for y. So it's really 600 minus 3 times 100 and divide it by 4. And so what is that? That's 300 divided by 4. And that should probably be a nice number. It's 150. I mean, we can do this. I don't need a calculator, right? So it's actually 150 divided by 2 because they're both even. And I know that's 75. So that's 75 feet. So we'll put a 75 there. And then finally, this number right here is the maximum area. So the max area is equal to 7,500 feet squared. So right here, we'll put 7,500. Right, but that's the idea. And hopefully you can see how these problems are similar to the ones we did in class, because I mean, basically 5's almost exactly the same. All right, so let's move on to what we're going to do today in this lecture activity. So we're moving on to rational functions and models. We talked about rational equations and inequalities in class, and today we want to talk about basically finding asymptotes and graphing what are something called rational functions. So first of all, what's a rational function? It's basically just a polynomial on top and a polynomial on the bottom. So examples of this, might be like, I don't know, x minus 5 on top, and then x squared minus 25 on the bottom. And so when you have these types of functions, notice sometimes they're not going to be defined. So we talked about this last time when we were solving rational inequalities. When you get 0 in the denominator, something strange is going to happen. That function is not defined. So in the problems that we work, a lot of times you're going to get what are called vertical asymptotes. So basically the function's basically going to blow up or blow down. You'll also sometimes have horizontal asymptotes because you have these leading terms that kind of control the function in the end. So as x gets bigger and bigger, like if x is, I don't know, like 1,000, when you plug 1,000 into this function, on top you get out 1,000, but on the bottom you get out like 1,000 squared. And so you'll see that 1,000 squared is going to kind of dominate the function and force it to 0. And that's how we get these what are called horizontal asymptotes. All right, let's just look at some examples, and this will become clear as how do you do these real fast. All right, so here's a lecture activity trying to understand rational functions here. And we basically have 4 rational functions. So take a look at them real fast. So here's the first one right here, just a polynomial over a polynomial. Here's the second one, again, just a polynomial over a polynomial. Here's the third, again, a polynomial over polynomial. And here's the fourth, polynomial over polynomial. You might ask, like, why do we have 4? Why not just 1? Each of these rational functions kind of tells a little bit of a different story. And so what we want to do with these rational functions is we want to first find the vertical asymptotes. Then we want to find the horizontal asymptotes. We want to find any x-intercepts. We want to find any y-intercept, if any. And then we'll use our calculator to kind of help us sketch the graph of these functions, and we'll make sure that we have to include all the intercepts and asymptotes. And so when we do this, make sure you use pencil because we are going to erase. We're going to make some good mistakes, common mistakes, and we're going to catch them in the end with our graphing calculator. So let's go back here to the first problem. And whenever you're working with a rational function, the first thing you want to do, if you can, is factor the top and factor the bottom. So right here, we'll go through each of these. This is just 2x divided by, on the bottom you can factor this, x minus 6 times x plus 6. This is a difference of 2 squares, we call this. Oops. Let me make this one a minus. I don't know why I made it a plus. So minus 6, then times x plus 6. And the reason why you want to factor the top and bottom is sometimes interesting things will happen. So what do I mean by that? Let's look at the next problem. So here's the next problem, and let's factor this guy here. So to factor this one, it's a little tricky. So up on top, how do you factor the top? Well, first I'd pull out the 2. So it's 2 times, and you have x squared minus 16. And then I can also factor the x squared minus 16, so that's going to be 2 times x minus 4 times x plus 4. And then we'll factor the bottom down here. And so that one was just kind of a little guess and check. So x plus or minus something, x plus or minus something. The somethings come from the 20, so I'm thinking that's probably 4 and 5. And then to get that plus one, I'll put the plus on the 5 and the minus on the 4. And so over here, we'll just copy that down. So you get x minus 4 and x plus 5. And so what did I mean by something interesting? Well, notice it has the same factor on bottom and top. So that's going to cause a problem later on. In fact, I'll tell you what it is right now, but we'll discover it with our calculator. That is a hole. So the way you put a hole into a function is you just multiply top and bottom by x minus wherever you want that hole. So real quick, for example, let me draw a nice looking graph. Let's draw this graph y equals x. suppose you would like to put a hole at my favorite number. So my favorite number is the number 7. So suppose you'd like to put a great big hole right here at 7. All right, so you want the same graph, we'll draw it in green, but you want a hole at 7. So how would you write that? Well, you'd write y equals x, and then on top and bottom, you'd put x minus 7. And then the green graph and the black graph would be exactly the same, because normally this would just cancel out, except at 7, because what happens when you plug in 7 to this? You get 0 in the denominator, so it's not defined there. And so that's basically how you put a hole in a graph. You just multiply top and bottom by the same thing. All right, let's go to the next one and factor it. And so this one, oh, it's already factored. You can't factor x squared. X squared is just x times x. And x minus 1, of course, is x minus 1. So that's good to go. And we come to the next one, try to factor it. Well, 10x is already factored. And now here's a tricky one. If you try to factor x squared plus 1, you can't. You can try x plus or minus something, x plus or minus something. The 1 here means it's 1 and 1. But there's no way to add and subtract the 1 and get a plus 1 on the end. So you could put plus or minus here, but notice when you multiply plus 1 by minus 1, you don't get a plus 1 back. So you cannot factor x squared plus 1. It is what's called irreducible. And it's irreducible because what does its zeros look like? The square root of negative 1. All right, so remember, if you take x squared plus 1 equal to 0, subtract 1 from both sides, you get negative 1, and take the square root, it is plus or minus. And so that's equal to plus or minus I. So you get an imaginary number. So this one can't be factored. We say it's irreducible, or if you want, it just can't be factored. So that one's good to go too. So the first thing you want to do is basically factor your rational function. And now we're going to go back and we're going to find what are called vertical asymptotes. All right, so how do you find vertical asymptotes? Well, what is a vertical asymptote? A vertical asymptote is where the function either blows up or blows down. In fact, let's just graph this thing in our graphing calculator, and you'll see right away what I mean by a vertical asymptote. So on your calculator, take it out, hit y equals for me, and clear that out. And we're going to plug this function, and we're actually not going to plug the factored form in, because if you made a mistake on the factored form, it'll show up when you plug it in. So we're going to plug in the original function. And so let's talk about how to do that, because here's where the first mistake sometimes occurs. The 2x is good. No problem with that. Divide by, but here's where your mistake occurs. You want to divide by what? You want to divide by this whole thing in the bottom. So you're going to have to put that in parentheses. If you don't put it in parentheses, it will not do what it should do. So left parenthesis x squared, and then minus 36. That just collects the subtraction together, saying do that first before you do the division. And then we really don't know what to make our window, so we would just do a standard window on this. So hit zoom and go to Z standard. And then you can see what we mean by vertical asymptotes. So right here where the function blows up and blows down, so blows up means goes up, blows down means goes up, goes down. Basically, they're going up to plus or minus infinity. So up is positive infinity, down is negative infinity. And same thing over here. And so you'd see that actually has two vertical asymptotes. Now, how do we find them? It's actually very simple to do. You just take the denominator and set it equal to 0. So that's how you find vertical asymptotes. So you take x minus 6 times x plus 6. And we got to show work, right? So we just say set equal to 0. And then after that, you can kind of do what you like. I like to then say, you know, you have this times that equal to 0. So that means this equals 0 or that equals 0. And so that means either x equals 6. You add 6 to both sides here. Or x equals negative 6. You subtract 6 from both sides. And so we get these two answers. And so what I can do, those are vertical asymptotes. So over here, I'll just put a dashed line and label that x equals negative 6. And I'll put a dashed line over here. And again, you don't have to draw to scale, just kind of shape and form. And so x is equal to 6. And that's how you find the vertical asymptotes. All right, let's do it again. So let's go to the next one. So let's find the vertical asymptotes on this one. So again, we just take that denominator and we set it equal to 0. So x minus 4 times x plus 5 is equal to 0. And so what does that mean? That means either this is 0 or that's 0. And so either x minus 4 is equal to 0, or x plus 5 has to be equal to 0. And so we add 4 to both sides and get x equal to 4. And we subtract 5 from both sides, get x equal to negative 5. And then we can put that into our graph over here. So I'll put x equals negative 5. And over here, this is where you need a pencil, because you'll see later on, this is actually a mistake, but it's a good mistake to make. We're going to catch it in the end. So I'm going to come back to it. But for right now, I'm going to put a vertical asymptote there. But remember, it's really a what? Really a hole. But you might not know that right now. So we'll come back to it because our calculator will catch that mistake for us. And then we'll come over here to the next one and set that denominator equal to 0. So x minus 1 equals 0. So just the denominator, because that's where it's basically undefined. That's where it's going to blow up or blow down. And we add 1 to both sides, so x equals 1. And so right here, I'll put a dashed line and write x equals 1. You have to label your vertical asymptote somehow. There are two ways to do it. You can label it like this, or you can just put a 1 right here. You do one or the other. Doesn't matter which one. And then finally, the last problem here, we set the denominator equal to 0, and you know there's going to be an issue because we just did this. So you try to solve this for x. You can't really factor, but you could move over the 1. So x squared equals negative 1. Take the square root of both sides, plus or minus the square root of negative 1. Oh, right, remember, that's a real imaginary number, plus or minus I. So this one will say there's no real solution, right? Which implies no vertical asymptotes, right? So none, basically. Right? And no real solution, you'll see this pop up from time to time in your math classes. It just means there's a solution. It's just not real, right? It's imaginary. Right? And so that kind of completes the picture for vertical asymptotes. So you can have rational functions that have no vertical asymptotes, that have just one vertical asymptote, of course, right? And then over here, you could have one that has a kind of like a pseudo vertical asymptote, because remember, we're going to come back and discover that's a hole. And then this one's kind of like the perfect situation. It's like it just has two vertical little asymptotes. And you can have more than two, right? You can have 3, you can have 4, but it becomes more complicated as you go. So that's how we find vertical asymptotes. Let's go down here and talk about now, how do you find horizontal asymptotes? So what the heck is a horizontal asymptote? So let's take a look at this graph again that we have up for this problem. And so horizontal asymptotes happen as you go out to infinity. So remember, there's two types of infinity: input infinity and output infinity. Input infinity says, go all the way out to positive infinity, like go all the way out to your right. Whereas output infinity means go all the way up. And there's also a negative infinity. So input negative infinity means go all the way to your left, whereas output negative infinity means go all the way down. And so if you look at this graph here, you can kind of see as you go to the right, it looks like it's heading towards height 0. And over here, it looks like it's heading towards height 0. And the way you determine that is you actually just look at the leading terms of the polynomial on top and bottom. And if the degree is bigger on bottom, it's always going to be 0. So we write this as y equals 0. And I'm going to use green, I think, here. So y equals 0. And the reason for that is because on the bottom, it's growing much faster than the top. So when you plug in a big number, like say you plug in 1,000, on top you have 2,000, but on the bottom you have 1,000 squared. And even that minus 36 doesn't change the fact that it's 1,000 squared. So the bottom is going to be like a huge number. And on top, it's just going to be kind of big, but not huge. Right? It's like you have pennies, you have 100 pennies on top, but you have $1 billion on the bottom. It just like dominates and heads towards 0. So this horizontal asymptote is y equals 0, because basically you have this 2x over x squared, and the degree is bigger on the bottom. So degree is bigger on the bottom. All right, let's look at the next case. So let's go over, here. And let's look at this one. So now let's look at the leading term. So here you have a 2x squared over an x squared. So you have a 2x squared over x squared. So guess what the horizontal asymptote is? Y equals the number 2. And that's because the degrees are exactly the same. So all we care about in that case are the leading coefficients. So it's like 2 over 1, which is 2. Right? So this is because the degrees are the same. So when the degree is the same on the top and bottom, the horizontal asymptote is just going to be the leading coefficient on top divided by the leading coefficient on the bottom. So that's case 2. So think about it. There's only really 3 cases. The degree is bigger on bottom, degrees are the same on top and bottom, or the degree is bigger on top, right? And that's the next example, right? So here's that example here. The degree, notice, you have leading term here and leading term here, and the degree is bigger on top. When that's the case, we just write none. And so here, the reason for that is look, you have x squared over x, and so the degree is bigger on top. So degree bigger on top. So there's 3 cases. Degree bigger on top will always mean none. If we go backwards here, degree is exactly the same. It's just the leading coefficients, 2 divided by 1, which gives us 2. If, we got to scroll down, if the degree is bigger on bottom, then it's always y equal 0. The bottom will dominate and force the function towards 0. And we should probably put these on our graph because we're going to have to. So I just draw a dashed line right here. So y equals 0. We'll go to our next graph. This was y equals 2. And give yourself plenty of room. So I'm going to move this up quite a bit because we're going to have to draw our graph eventually. Need lots of room to draw, basically. So y equals 2. And then over here, you have none. So there's nothing to draw. And then finally, this last one, notice what's going to happen here. Well, here's your leading term on top, leading term on the bottom. So it's like a 10x over x squared. And so you see the degree is bigger on the bottom. So degree bigger on bottom. And this is just me kind of thinking. You don't actually have to write this down if you don't want to. And so what does that mean? That means y equals 0. The bottom dominates and forces the function to 0. So what we'll do is draw a dashed line right on the x-axis, which is y equals 0. All right, and then we'll go backwards here. And again, you don't actually have to write this part down. You just have to give me the answer. And same thing back here. You don't have to write that down. You just have to give me the answer. So horizontal asymptotes are really nice. You just have to give me an answer. Whereas for vertical asymptotes, you do have a little bit of work to do. You have to show it's equal to 0 and solve that quadratic equation. And then over down here, again, you don't really have to do this part, but you definitely have to write y equals 0. All right, so we got the vertical asymptotes. We got the horizontal asymptotes. What's left to do? We have the intercepts. So x-intercepts, how do we find them, if any exist at all? So I always have to think a little bit, like, what do you mean x-intercept? Oh, it's where you cross the x-axis. So what does that mean? I don't know how far over you went, but I know you went up 0. Ah, the output is 0. So I'm going to take the function here, and I'm going to set it equal to 0. So I take that function, 2x, divided by, and you can take the factored form if you want, although it's not going to matter, but x squared over 36, and I set it equal to 0, so there's the first step. And now I have to solve a rational equation, right? So how do you solve a rational equation? We just clear the denominators, but these are always very nice. And they're very nice because when you clear the denominator, on the right-hand side, it's 0 times it. And 0 times anything is 0. So you basically just 2x on the left and 0 on the right. And then divide out by 2, so you get x equal to 0. So there's one x-intercept. So I'll come up onto my paper here or my graph and put, there's my x-intercept. And then we might as well do the y-intercept at the same time, because remember the y-intercept, well, if the output's 0 for the x-intercept, you can almost tell, oh, the input is 0. You don't know the output, but you know in goes 0. So this is just going to be f of 0. And so you're going to plug in 0 instead of setting equal to 0. So here, let me zoom out just a little bit so we can see the function. And so I'm going to plug in 0 into my original function up here. And so what do I get? I get 2 times 0. I just like to show my work. So if I make silly mistakes, it's easy to spot. easy to get partial credit. And I get 0 on top and negative 36 on the bottom, which be careful. A lot of times, excuse me, students like to say that this is undefined. No, 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 no. This exists. It's 0. Negative 36 goes into 0 times. All right, so it's just 0 here. So what we like to write then is y equals 0. All right, so make sure you write y equals versus up here we write x equals. And so this is actually the same point right there, right on top of the blue point. All right, let's transition and do this again over here. So go to the next problem. And we want to find the x-intercepts and the y-intercept. And we'll zoom out just a little bit to kind of pull this all together. And so for the x-intercepts, remember what we have to do. We just take this thing and we set it equal to 0. And I'll take the factored form because the top's already been factored, which is nice. It's really only the numerator that contributes to x-intercepts, but I like to set it all equal to 0 because that's how you do it in general. And so you take the whole function, you set it equal to 0 because that's when the output is 0, and then you just clear the denominator. And once you clear the denominator, it's just going to go away. So x minus 4 times x plus 5. So just multiply by it on both sides. And so what do we get? On the left-hand side, you're left with just that numerator. So you have 2 times x minus 4 times x plus 4. And then on the right-hand side, we just get 0. And so again, you're like, oh, look, I have 2 things. I have basically this times that, and I guess you have this over here, and you're multiplying and getting 0. So you know one of those things has to be 0. So either x minus 4 equals 0, or x plus 4 is equal to 0, which means basically you add 4 to both sides. So you get x equal 4. And here you subtract 4 from both sides, so x equals negative 4. And so we go up on our picture here, we put a point, right? That's at negative 4. So I have a 0 there. And then, I come over here, and that's supposed to be a 0 too, but I have a vertical asymptote. What is going on? And you say to yourself, remember, it's a hole. But we'll leave it for right now. We're going to come back and correct all this one in a minute. So we'll just leave it for right now because that's what we found. And then finally, for the y-intercept, we're just going to plug in 0. So f of 0 is equal. And we come back up here, and it's easiest to plug into this one. So it's 2 times 0 squared minus 32. And then divided by, on the bottom, we have 0 squared and then minus an x. So you got to be kind of careful. I kind of hid the minus from us right there. So let's just erase. I'm hiding the function. So let's erase that so we can see it again. So it's minus x, which is really minus 0. So put a minus 0 there. And then minus 20. So that's equal to, now be careful, because you just get negative 32 on top and negative 20 on the bottom. And that simplifies. They're both negatives, so the negatives are going to cancel. And they're both even, so you get 16 over, what is that, 10? Oh, and you keep on going, they're still even, so that's 8 over 5. So it has a y-intercept at 8/5, which is smaller than 2, so we'll put our 8/5 right about there. And again, it doesn't have to be drawn to scale, and we'll label it. So it's 8/5 basically. And that's it. That's our y-intercept. So we should write y equals 8 over 5. And so there's our answer for our y-intercept. Okay, almost done. Just a couple more intercepts to find, and then we can graph all these guys. So let's come down here and find the x-intercept for this one. All right, so how do we do it? Well, you take that function at x-intercepts, you just set it equal to 0. So take this x squared over x minus 1, set it equal to 0. We'll clear the denominators. We multiply everything by x minus 1. So on the left-hand side, you just get an x squared. On the right-hand side, you just get a 0. Take the square root of both sides. It is plus or minus, but that's always 0. And so right here in my picture, you can label that to origin 0. There's an x-intercept. And then finally, for the y-intercept, you just plug in. What's f of 0? So you come back up here, plug in 0 for x, so 0 squared over 0 minus 1, which equals 0 over negative 1. And again, be careful. This is well defined. How many times does negative 1 go into 0? 0 times. And so my y-intercept is at y equals 0, which is the same point. Right? When you have an x-intercept at 0, you will always have a y. Or when you have x-intercept at at 0, 0, right? You also have a y-intercept at 0, 0. Okay, one last one. So where's this last one at? Here it is right here. And so we want to find, again, x-intercepts and y-intercepts. And so we're going to take this. And remember, when you're writing this down, make sure you write down everything I'm writing down here. So we take 10x over x squared plus 1. We set it equal to 0. We clear that denominator, x squared plus 1, on both sides. And so we wind up with a 10x equal to 0. We divide out by 10. And so we get x equal to 0. So we'll put that point right on top there. And finally, for y-intercepts, we have f of 0 equal to, and we just plug in 0 here. So you get 10 times 0 over 0 squared plus 1, which 0 over 1, which remember, that's actually a nice number of 0 because 1 goes into 0 0 times. And so now I know y is equal to 0. So there are my two answers there. You could put the dot right on top of it or just leave it because they have the same intercept at that origin. Okay, so we now know the intercepts. We have what we think are the asymptotes. The rest of this is solved with our graphing calculator. So go back to the first problem. We already put this into our calculator, so we just need to turn this back on. And we just mimic the behavior. And I say mimic, not exactly though, just as shape and form. So look at your calculator and notice how the function's behaving. So over here, it just starts up and goes down. It looks like it's vertical, but it's never vertical. So remember, these are just representations, and the programming on your calculator is a bit flawed. So when you graph this, you have to graph it just like that, right? In fact, I don't even like that. Kind of going up, down, and then stop, right? What you don't want to do is this, and this is what you guys often do. You'll start and you'll go down, you'll start going straight, and then sometimes you go back on yourself like that. That's not a function. So notice for an input, you don't get just one output, you get two because you get an output down there. It basically hits it twice. It'll hit it here, and it'll hit it down here again if you draw a vertical line. So you have to be very careful when you do this. So when you draw these, you've already put the asymptotes on there, so you don't really have to give me too much more information. That's it. That's all you have to give me. And then over here in the middle, you look and see what's happening. So you see it starting up and coming down. And then again, it looks vertical there. It's not vertical. And it looks horizontal. It's not horizontal. So what you want to do is just use that to kind of help guide you. And then stop once you get close to that asymptote. Right? Don't go straight down. Don't go horizontal because it's not really going horizontal. It just looks like it because the calculator can't graph things that precisely, right? Because it's using little dots, right? So it has to kind of like make adjustments to make it look like something, basically. And those points should be connected right there, right? All right, and then the last part, you just look over on the other side, and you're like, oh, yep, starts up here, right? Comes down here. So start up and comes down. And then stop when you get close to that horizontal asymptote. Don't go all the way out, because when you guys go all the way out, you know, sometimes you guys come back up like that. You're like, oh, but I meant all the way out. I know what you meant, but you came back up. It never comes back up. It stops right there, right? That's good enough, right? I know the behavior is then determined in the end by the horizontal asymptote you drew right there. And notice you can cross horizontal asymptotes. Sometimes you guys don't think you can cross it. And I'm like, yeah, you can. Yeah, you can't, you don't cross, you know, it gets closer in the end, but it can actually cross a horizontal asymptote. All right, let's look at the next one because the next one is the tricky one. So on my calculator, I got to change this one. So on here, hit y equals and clear this out. And then we're going to plug this in. So on top, you're going to have to put parentheses on top and parentheses on the bottom. And we always like to put in the original one because if we made a mistake, we'll be able to catch it. And so I'll put a left parenthesis here. If I can make my buttons work. There you go, left parenthesis. And I'll type in 2x squared and then minus 32 in parentheses divided by left parenthesis x squared and then plus x and then minus 20 in parentheses. And then we'll just do a negative 10 by 10 window again, guys. So, you know, it's already set up, but if it wasn't set up, I would go to zoom, Z standard, and then hit enter, and let's see what happens here. Because something weird should happen, because remember, we have a hole, I told you. So notice, there is a vertical asymptote here, but there's none over here, because why? There was a hole. So we need to go back and correct some of our work on this one. So on this one, we're going to come back and we're going to put an X through this one right here, because it's not really a vertical asymptote. And then over here, we have to erase that. So kind of come up here, erase that there, erase that down there. Because again, this one's actually a hole. And we'll come down here at this x-intercept too, because we had to erase that too. So right here, x equals 4, we'll put an x on that because again, that's a hole. So we had to x those out because they're not really intercepts or asymptotes. And so when we come back up here, at 4, we do have something though. We have a hole. So what I'm going to do is I need to draw a hole, but how do you find the height of the hole? So this is the tricky part. And so what you want to do is you basically want to cover up, you can't see my hand on here, but you want to cover up this x minus 4. So basically, cover up the x minus 4, ignore it basically, and then plug in the number 4. So what do you have left over? You'll have a 2, and then a times, and you have a 4 plus 4. And on the bottom, you have a 4 plus 5. And so on top, you're going to 8 times 2, which is 16, and on bottom, you have 9. And so that is the height at the hole. So when we make the hole, it's 16 over 9, which isn't quite 2. You make it right here. It's at 4 comma 16 over 9. And you guys always ask me, how'd you find this 16 over 9? I'm like, listen, I just covered it up. Just cover it up. Don't look at that piece. Use the rest of the function plug in, and that'll be the height. Okay, that's what you do. Just cover up the x minus 4s. All right, let me fix this here. All right, so there are my dots now. Everything's good, so I should be able to connect my dots. So I take a look again at my picture here. Don't miss this left-hand side. So it starts in the bottom and goes up. So we got to be kind of careful. You can't see it because I'm going to cover it up, right? So in order to do this, I am going to have to move some stuff just a bit here because I do want you guys to see what I'm doing here. So I'm going to move this up just a bit. We'll make this a dashed line right here. And now I can draw it. So it starts down here and then goes up. And again, you don't have to go vertical. You don't have to go horizontal. You already had the vertical asymptotes there. They're telling me what to do. And then I go back to my calculator and say, what happens next? We see how it goes down, then comes up. And so I'm going to do that over here. And I'm going to do it in a way that I kind of miss some of the points. Oh my goodness, I missed the points. So what do? Well, you use erasable marker or pen, and you can just erase the point. So right here, man, that's big. I can erase it, and I can redraw it. There it is. And over here, I can use this eraser. It's small. Just erase it right there. And there I put a hole. So, hey, I'll just erase it, put a hole right there, and I'll color it in blue. So there's my hole right there. And I already labeled it, so it's fine. That label can just stay right there. It's good to go. So there's my hole, and you're good. All right, that's what that graph looks like. So don't be a prisoner to your points. You can, draw the graph and then erase your points and put them where they are and just label them, and you're pretty much good to go on that type of problem. All right, so that was the last really hard one. Let's go to these other ones here. They're actually a little bit easier. And so on your calculator, we'll plug this in. You will, so clear this out, y equals clear out. You will need to put parentheses on the bottom down here though. Change this. So you will need to put parentheses down here on the bottom. And so on my calculator, what do I have? I'm going to hit y equals. I cleared that out. I'm going to type in x squared. Oops, not that one. So x squared, and then divided by left parenthesis x minus 1 in parenthesis, and then just go to your graph because you already have a negative 10 by 10 window. And so that's what it looks like. Kind of weird. So we'll talk a little bit about why it looks so strange here. So basically, what does it do? It kind of starts here, comes up, then turns radically and comes down. I don't like how I came down there. I don't see, it looks like it kind of coming back on itself. So I'm going to erase that little piece right there. And that's why, again, we use pen or pencil that you can erase. And I come down and I stop. All right, so just stop. Again, I don't even like that. So come over here, down, stop. All right, and then I do the same thing up here. I can start up, try to come down, back. And again, I don't like that either. All right, so you got to be very careful because you don't want it to go back on itself. That's good enough. I don't want that thing to go. What you don't want is you don't want it to go back like that. When it goes back like that, it's no longer a function. So you got to be a little bit careful when when doing it. Oops, I erased it. All right, so bound. There we go. All right, and so you can look and just get the overall shape and form. And this one's kind of tricky. So I'm going to talk about this, but I'm not going to ever test you on it. This one actually has what's called an oblique asymptote, which is kind of a weird thing. There are other types of asymptote. So asymptote just means forever getting close to. And so this actually has what's called an oblique asymptote. And oblique just means one that's not vertical. And again, I'm not going to actually ever test you on oblique asymptotes or ask you to find them or anything, because in order to find them, what do you actually have to do? You actually have to, well, the way that they occur is they come from when the degree is bigger on top than when on bottom. And when that happens, you have to do what's something called dividing the polynomial, which we don't do a lot of dividing polynomials here by design. But it will come up in other classes, like if you're in Calculus 2, we don't do much of it in Calculus 1. But if you divide these polynomials, you'll actually see that you have a remainder here of x plus 1. So it's actually equal to line y equals x plus 1. But again, I'm not going to ask you about oblique asymptotes. And then finally, let's do this last one. So this is an example with no asymptotes. So what does that look like? So on your calculator, again, you'll have to put the bottom in parentheses here. So take out your calculator and just plug it in. So y equals, clear this out, and you get 10x. And then divided by, and then left parenthesis, x squared, and then plus 1. We'll hit graph and see what it looks like. And then we'll just kind of use this as a guide. So, you know, it just goes down and comes back up and goes back down. So the best that I can kind of comes down, goes back up. And then it basically does the same thing on the other side. So again, the best that I can goes down. And I'm going to stop right there. And if I don't like the other side, like I like, that's like a little like kind of a hiccup over here. So I'm just going to erase this right here and then put an arrow on it. Again, that's why I use something that's erasable. So then I can, you know, make silly mistakes and then correct it. That way it doesn't look like it's going back up ever. And that looks good. I think I'll take it. All right. And so basically that's it for rational graphing rational functions. And I'll see you guys on Monday.